In this video, we are going to be talking about oxidation states. So when we normally calculate the formal charge of an atom, we think of the bonds as being covalent. So this carbon and this oxygen would be sharing the electrons of the bond equally. And if we were to break the bond, we would break it homolytically. So each electron would go to one or the other atom. And so if we were to calculate this formal charge, carbon wants 4 electrons, and if you box off the electrons that it does have because it shares them all covalently, then this carbon would have 4 electrons in its valence shell, and that would give it a formal charge of 0. But when we're calculating oxidation states, we treat the electrons a little differently. So we are going to treat the bonds as ionic, and we are going to break them heterolytically instead of homolytically, except for carbon-carbon bonds. So what that means is that each atom is going to get a pair of electrons, not one electron. And this is based on electronegativity. So oxygen is very electronegative compared to carbon. So there are 2 electrons that are in the bond between this carbon and oxygen. And so when we are looking at the oxidation state, we are going to say that oxygen is going to get both of these electrons because it wants them more than the carbon. But when we're looking at the carbon-hydrogen bonds, carbon is more electronegative compared to hydrogen, so it is going to get both of the electrons from the bond. So then when we're calculating the oxidation state, we are going to do that in the same way that we calculate formal charge. So carbon wants 4 electrons, but if we box off the electrons that carbon actually has in this situation, it has 1, 2, 3, 4, 5, 6 electrons, and they are all coming from the carbon-hydrogen bonds. So we are going to subtract 6, and that will give us an oxidation state of -2. So now we're going to talk about the acronym Oilrig, which I'm sure you've heard before. Oxidation is losing electrons, and reduction is increasing electrons. So we're going to look at an example of an oxidation reaction and then a reduction reaction. So in this case, we have carbon bound to 4 hydrogens, so methane. And if we calculate the oxidation state for this carbon, like we said earlier, carbon is more electronegative than the hydrogens, so carbon is going to suck in all of the electrons from each of these 4 bonds. So it's going to get 1, 2, 3, 4, 5, 6, 7, 8 electrons. And if we actually do the calculation, carbon wants 4 electrons, it has 8 electrons, and that would give it an oxidation state of -4. So now if we look at the product over here, after we oxidize it, this oxygen is very electronegative, so it is going to take both of the electrons from this bond right here, and then again, carbon is going to get all of the electrons from the carbon-hydrogen bonds. So carbon wants 4 electrons. In this case, it only has the 6 from the carbon-hydrogen bonds, so we subtract 6, and that gives us an oxidation state of -2. And you can see that this is oxidation because in the case over here, the carbon has 8 electrons, and then in this case, it only has 6 electrons. So it's losing electrons, and you can see that the number for the oxidation state is increasing. It went from -4 to -2. So now we're going to look at an example of a reduction. So here we have carbon dioxide, carbon doubly bonded to 2 oxygens. So again, oxygen is more electronegative. There are 2 electrons in each bond, so the oxygens are going to get all 4 of the electrons from the double bonds. So that leaves this carbon with no electrons. So carbon wants 4, it has none, and that leaves you with an oxidation state of 4. And now if we look at this one right here, same thing, this oxygen is going to take all 4 of the electrons from this double bond. The carbon is going to take the electrons from this hydrogen, and then is also going to lose the electrons to this oxygen. So now this carbon has 2 electrons. So it wants 4, it has 2, and that leaves you with an oxidation state of 2. And you can see in this case, it has no electrons over here, and then it has 2 over here. So reduction is gaining electrons, so this carbon gained electrons, and in the process, the oxidation state went from 4 to 2. So the actual oxidation state decreased. So here are some general rules for oxidation changes of carbon. If we are oxidizing a carbon, we are adding oxygen, molecular oxygen, we are adding a halogen, or the loss of molecular hydrogen. For reduction, it's the exact opposite. It is the addition of molecular hydrogen, a hydride, or the loss of oxygen or molecular oxygen, or the loss of a halogen. But in these cases right here, it would neither oxidize nor reduce the carbon. So if you add a proton, a hydroxide, water, or a hydrogen halide, it will neither oxidize or reduce it. So go ahead and pause the video and see if you can determine if each transformation here is an oxidation, reduction, or neither. All right, so here are the answers for this. For this one right here, I actually drew out all of the electrons as little dots. And you can see that with this oxygen right here, it is more electronegative. So all 4 of the electrons from the double bond are going to get taken up by that oxygen. And then remember, for carbon-carbon bonds, we treat them as covalent. So the bond has 2 electrons. 1 electron is going to go to one carbon, and 1 electron is going to go to the other carbon. So that's why we split this bond in half right here. So in this case, the carbon only has 2 electrons. So it has it wants 4, it has 2, and that gives you an oxidation state of 2. And then same thing over here. Chlorines are more electronegative than the carbon. So the chlorines are going to get both of the electrons from each bond. And then this carbon is only going to get 1 electron from each bond. And then again, the oxidation state is going to be 2. So it is neither going to be oxidized or reduced. In this case, the oxidation state is 1. We are increasing the oxidation state. So this would be an oxidation. And then for the third example, we have an oxidation state of 3, and we are decreasing the oxidation state, so we are reducing it. I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.